Hello React Native EU. I am Juha Linnanen from Finland, the head of mobile development at Gopher, and I'm thrilled to be at this conference again. I have been at all the previous editions of React Native EU, but this is my first time presenting. I'm a mobile developer with a native background, but the past 3+ years I have been using mainly React Native as my tool of choice for mobile development. Gopher is one of the leading IT consultancy companies in Finland, with over 600 employees, offices around Finland and also in Germany, Spain and Estonia. For mobile, over half of our projects are utilizing React Native, and we are quite happy to have it as our main mobile development tool. Today, I will take you on a journey with me on how we ended up using GraphQL on a React Native app, what kind of challenges we faced, how we solved them, and what was the outcome. The app in question is Yle Uutisvahti, which is a news application for the Finnish public service broadcasting company. For an app that basically targets only Finland, a country of 5.5 million, the app is quite popular. It has over 200,000 active weekly users, sending millions of push notifications each day. It is allowing the users to personalize the kind of news they are interested in and receive notification for the most important news for them. The app was first developed in 2013 and has won multiple awards, such as the Best Mobile Service in Finland 2014, as can be seen from the newspaper clip. The app has been under development for a long time, and the age was starting to show in the code. Features had been added here and there, and code had become complex. There was feedback on the app not always starting up properly. Sometimes the screen would just stay white, like in this picture. Developers agreed that the startup process is the culprit. This was one of the first tasks I started to look at, and it indeed was complex. It took me a couple of days to grasp what was going on. There were so many steps, which each could lead to some hard to handle error cases. I identified over 15 API calls being made, which contributed to the complexity. The app was using Redux for state management and Redux sagas for async operations, so Redux was heavily involved trying to keep local and remote data in sync. It was clear that we wanted to try and simplify the startup process, but how? This is when I remembered GraphQL. I hadn't used GraphQL for a real project yet, but I had attended GraphQL Finland conference, been reading about it and playing around with it. This gave an idea that maybe, just maybe, GraphQL could help solve the startup process and at the same time help the app's state management and data syncing elsewhere too. There will be roughly 5 topics I cover today, which go through the lessons learned during this migration. First, how the proof of concept was built and basic usage of Apollo in a React project. Second, how we ended up loading article data using local resolvers. Third, an example of how to use type policies with Apollo cache. Fourth, local state management using React variables. And fifth, how to debug and test React components using Apollo. So let's start with the proof of concept. The change to using GraphQL would be a pretty big change to the application. So we didn't want to be too hasty with the decision to go through with it. Initially, I decided to make a proof of concept for just a startup, how it could work using GraphQL. My goal was to make it simpler with fewer API calls. The proof of concept was implemented as a separate React Native TypeScript app with then brand new Apollo Client 3 early beta release. For backend, Apollo Server 3 was used to do a quick and dirty GraphQL gateway. We had our current architecture that needed to keep working. So the gateway was built as a separate service, which behind the scenes used Apollo data REST source to query the REST APIs in place. This made it quick to test out GraphQL with real APIs without breaking changes to the current setup. I worked hard on getting the proof of concept ready within a week to show that it would be a viable solution and something worthy of investing more time as a real solution for us. The finished proof of concept had a much simpler and working startup flow. although not all real apps functions. Being able to browse the list of articles and even read some of them. Much of this was possible due to the nature of GraphQL and Apollo client. In the end, there were 1 or 2 API calls. One mutation to register the device for the first time. Second, to receive the articles and user info. Preferences query is able to combine multiple separate REST API calls. Queries are your typical way to get data from the backend. Mutations are used to modify the backend data. So, how do we use these GraphQL operations using Apollo client? There are 3 very handy hooks available. UseQuery is the basic hook to make queries to receive data. It gives you back data, error, and loading objects, which can be used to then populate the UI however wanted. UseQuery is run right away when the component is mounted. UseLazyQuery also runs queries, but not right away. Instead, get back a function that can be called to make the query to be run. This is useful when you need to run the query only as a reaction to something. For example, when a user presses a button or when another async call is returned. UseMutation is used to update backend data, and similarly to UseLazyQuery, gives you a function to run. That function will take the variables the operation uses as an argument. For example, registering the user, we pass device token and user ID to the registered device function. Here is a small example app illustrating how we can use the Apollo hooks. On the left-hand side, we have a Hello EU query. We have a Hello React component that uses the query through UseLazyQuery. This is so that we can make the query only when the user presses the button. After we have the data, it is displayed to the user as shown on the right screenshot. Now, not everything was as easy as using the hooks. First challenge was persisting the cache. We wanted to save the user info so we wouldn't do the registering mutation again next time the app is started. This meant we wanted to keep the user ID and device token persisted. Apollo client can handle local state management as well, so it was used for the user info and using cache persistence to save it. Apollo client itself doesn't have a persistence built in, but there is a Apollo cache persist library. It doesn't support version 3 out of the box, at least not yet, so for the proof of concept, a workaround was used. We try to read the user info inside the cache, and if there is an error, meaning persistent data doesn't exist, we write the initial data ourselves there. Also, we add on reset store callback to write the initial data there as well on reset. This way the data is always initialized properly. This does add an extra async step to the setup, which is an awkward inside the React component and leads to a bit of a complex use effect hook solution. I have been talking to Apollo client developers and it sounds like rethinking persistence is on the roadmap, and if it was baked into the library, there would be a way to get the initial data setup much cleaner done. Article data has content, which is represented by an array of content blocks. Example blocks would be heading block, text block, or image block. You can see how the union is defined in the backend. This did not work out of the box on the Apollo client side, but required configuration. Also, Apollo Client 3 has changed how the configuration happens. Now one can define possible types within in-memory cache and give the type names that some types can be. Here we do it manually for content blocks, but if you would have a lot of possible types needed to be defined, Apollo documentation shows a way to generate the possible types from your schema automatically as well. Next, when querying content, we cannot query fields directly, but we need to have split the inside using fragments. Here they are inlined. This is needed as not all the fields are available in all the possible types. For example, level is only available on heading block and caption on image block. One thing to make the development much more fun and easier is the GraphQL playground, which Apollo server has built in for development builds. It allows you to easily make GraphQL operations against your GraphQL endpoint. My typical workflow involves trying out the queries first in the playground, and once I am satisfied, I will copy them over to the code. It was also priceless in developing the proof of concept backend to test changes fast. I find this to be an excellent development experience and real boon for using GraphQL in my projects. After proof of concept and getting a go-ahead, we needed to consider the backend solution. It was decided to create a new backend GraphQL API. Instead of Apollo server, which was used for the proof of concept, a JVM-based GraphQL server was chosen for the interop with the rest of the backend. We also made the decision not to make article data accessible through GraphQL API, but keep it as a separate REST API. This was a highly optimized and cached endpoint, which we needed to work flawlessly. Getting article data to Apollo server with Apollo data sources worked really well, but since we needed to get them now on the client side, we had to do it differently. We still wanted to keep GraphQL as the abstraction and not have components make REST API calls. We decided to try to accomplish this by using local resolvers, which allow you to have queries in the field that are not represented in your remote GraphQL schema, but are only on the client side and resolved by the local resolver. First, we do the REST API call on the client within a local resolver to fetch the articles data using Axios. Second, we enforce the data, and third, we write the resulting data manually to the cache. Why the need to enforce the data fields? At first, this worked great without it, returning simple dummy data. But when trying with real articles data, nothing came through and there were no errors. Apollo was silently dropping the response as it didn't contain all the fields requested. Articles data has lots of fields that are optional and they might be missing completely from the response. We needed a way to make sure those would be at the very least present with the value of null. In addition, we wanted to add the __ type name to the response objects. Apollo uses the type name to know the types so that it is able to normalize and properly match the objects to the right types. For this, we build a function called enforce response schema, which takes the data and a response schema where we can specify all the fields the response should have and their default values if they are missing. For example, here we have the schema for image block, making sure that caption is always there with the default value of null, etc. How does the enforcement happen? It is a bit convoluted, so the code is not easy to show here, but it is using JavaScript proxies under the hood. Overall, we got some good learnings from loading the articles using local resolvers. Data enforcing was trickier than it first looked. Knowing that we know now, we might not have gone this route. Also, now that Apollo Client 3 is out, local resolvers are officially deprecated, which makes this solution not best for the long term. Field policies and reactive variables are Apollo Client 3's new way to do local state, and more on this later. There is, however, a difference how they behave compared to local resolvers. They are not able to return promises, so they cannot do async operations the same way than with local resolvers. This leads me to think using Apollo Link REST, a library meant to query REST endpoints within Apollo queries, or building a custom Apollo link would be most likely the proper solution. But since we now have a working solution, we haven't had the time to check these options yet, but we might later. Third, let's look at the Apollo's cache and how we can customize querying from the cache with type policies. Apollo has a very powerful cache where it stores the data that it has received. It uses data normalization to optimize reading and updating the graph as your application changes state. Here you can see part of our cache after the articles query has finished. We have the query and then articles objects which contain data on the articles. We need this extra structure in our case because article query has concepts and extra data which we need to access as well from article. This led to an interesting challenge. After we have fetched the articles and they are in cache, when the user goes to read a specific article, we'd like it to be read from the cache. We can make the query on the left-hand side, but if read the article object directly, we don't get the article query extra data, concepts and extra. We actually want to return the corresponding article query response instead of article. Luckily, type policies are quite flexible, and there was a pretty nice solution to solve this challenge. We can customize the ID value for article query using the article ID. You can see this done on the right-hand side by defining keyFields for article query. It has a special square bracket syntax in order to be able to refer to its children's values. This we need since we want to use the article's ID as the key value for article query, the parent field. After we have done this, we can refer to it in our query type policy for article. We receive existing data, arguments, and to reference function. We return existing data if it exists. Otherwise, we return reference to the correct article type entry in the cache in order to get that concepts and extra data. Okay, as I mentioned before about local state management, Apollo Client 3 introduced a new way of doing local state management other than local resolvers. Reactive variables became available during the beta phase and looked like a really interesting improvement, so we wanted to try them out. It helps me a lot to divide cache in 3 different types. There is remote state, which is coming from the backend. Apollo queries are a good match to handle those. This way, we are not required to manually try to keep the data in sync with the backend, like with Redux. Then there is the local state, which is a state that should be available in many screens of your app, but something you don't want to store to the backend. Reactive variables are good with this kind of data. Last, there is component state, which is the state only needed within the React component. These are best handled with React hooks and don't need a separate state management system, in my opinion. So, what are reactive variables for Apollo? They allow you to store local state outside of the Apollo client cache. And because of that, they can store data of any type, not just something defined for the cache. They are also available for you outside of interacting with the cache. But the huge upside is that any GraphQL query that depends on a reactive variable will be automatically updated when the value of that reactive variable changes. I find this to be a perfect fit for React application, bringing ergonomics for the local state, but keeping the reactivity of React. Creating variables or reactive variables is easy. Import make_var from Apollo client and use it to create your own reactive variables. Make_var takes the initial value as an argument. Important to notice that the return value is not a variable, but a function. This allows you to read and modify the value afterwards. To read the value of a reactive variable, call the function returned by make_var without any arguments. This returns the current value. It is important to know that this returned value itself is not reactive, but whatever the value was when this function call happened. For this reason, in React components, the best way to get the value is by querying it with the @client directive. Cache then needs to have the field read function defined in type policies, which will return the value of the reactive variable, like user_var in the example. Now, if the user is updated anywhere, Apollo will trigger an update to the getUser query in the component, which will update the component with the updated value, and the UI is kept up to date. To update a reactive variable, again call the function returned by make_var, but this time pass the updated value as an argument. Here, for example, we update the user to have an ID of Juha and accepted privacy policy version of 3. So after you have specified the read function for a field in cache policies, you are good to go and start using the values inside React components. Typical use case to display a reactive variable in a React component looks something like this. First, you make the query. Notice the @client directive for the user, which tells Apollo to only look on the local state side and not send that part over to the backend. Second, define the useQuery hook, passing the query to it. It returns then an object with data which has the user info. Third, now you can use the data to run some logic and render the value to the UI. Here we have a text component displaying the accepted privacy policy version. And that's it. Now this is a fully reactive, so no matter where or by what the accepted privacy policy version gets updated, this component is sure to re-render and display the correct value. If you end up using the same reactive variable in multiple components, it is easy to extract that query and use query as a custom hook. One thing we noticed is that we needed to manually handle the persistence of reactive variables. Reactive variables are not stored within Apollo's cache, so even if you persist your Apollo cache, reactive variables won't be persisted. Our current workaround is to update the latest value to async storage every time the value gets updated. For example, here we update the accepted privacy policy. We make a call to store user, which is a function that handles saving the value to async storage. When the application is starting up, we manually go and fetch those keys and call the reactive variables with the persisted values, rehydrating the variables. This is an area where, in my opinion, Apollo could work on to make it easier and have a built-in way to specify that you want a reactive variable to be persisted. Luckily, from some talks with the Apollo developers, it does sound like they acknowledge this too, so I'm hopeful this will happen in the future. So one very important part for the developers is how they can debug their code, and GraphQL is no different. Apollo provides developers tools for the client, but unfortunately they are not directly compatible with React Native Chrome debugging. For React, Chrome DevTools will pick up Apollo and have the tab shown for it. This doesn't work with React Native as the tab never appears. Luckily, React Native Debug, a dedicated debugging desktop app which contains the Chrome DevTools as well, has built-in support, and the Apollo DevTools will be shown in the tab. During the version 3 beta, this was broken for a while, but since the final release, it seems to be working. Here you can access all the features that the DevTools provide, which include GraphQL, which is the GraphQL playground, where you can run GraphQL operations and see the output. Queries and mutations, see what queries are being executed in your app and which components are running them. And cache, see what is inside your normalized Apollo cache, which is now showing the articles in here. These are very useful for debugging purposes, especially seeing the state of the cache has helped out many times. After React Native 0.62, many prefer debugging React Native apps with Flipper, which is an excellent debugging tool provided by Facebook. I got into thinking whether it would be possible to run Apollo Client DevTools as a Flipper plugin. I posted it as a feature request and many seemed excited for this to happen. The DevTools are now in the process of being remade, so it might be a good idea to wait for that to be finished before working on the plugin. But I wanted to try it out anyways already, so I forked the DevTools, and after a while of tinkering with it, there is now an alpha version that has the cache store tab working, which can be seen here. If you are interested in getting the rest to work as well, feel free to come and contribute. Testing is also an important area to consider, and it was pleasant to see this was considered well from Apollo. They provide a mock provider component, which we use in conjunction with React testing library's React Native version. Mock providers, mocks are request result pairs. So first we specify what the request should look like, and if that matches, mock provider will give back the result as a response. Once we have a mock provider, we can create a wrapper that can be used for the components that we want to test. For a simple example, here we have a React hook which has a GraphQL operation inside. We use React hooks testing library to render the useLogin hook, wrap it in a wrapper that provides the mock response. This allows us to assert what the response from the operation should be. There was one gotcha that took some time to realize. Mocks given to mock provider didn't work for local resolvers. This is related to the issue that if the mock is not working, there was no warning or error to see what was wrong. Maybe some variable doesn't match 100%, not sure. So it was very hard to debug why the mock was not working. Luckily, it is possible to also pass resolvers to the mock provider with the resolvers props. This approach works with local resolvers, but all in all, I would have preferred a unified way and better debuggability when it comes to testing Apollo operations. Okay, we are coming to the end of our journey together. The application itself is not all done yet and is still under active development. But so far we have been quite happy with using Apollo and GraphQL for handling remote and local state in the Uutisvahti app. Here is a screenshot of the application right now. For the outcome, I want to highlight 3 areas especially. API interface became super clear. GraphQL schema coupled with TypeScript, you will know exactly what data you are receiving and what input variables are required for a mutation. You can also easily test these out on GraphQL Playground beforehand. There are no issues of over or underfetching, and we are able to reduce the amount of API calls in the startup of Yle Uutisvahti from 15 API calls to just 1. Compared to our old state management solution using Redux, which had remote state, local state, and component state all bundled in the Redux store, there are now much better boundaries, and each kind of state is easier to work with and test for. This leads to the third point. The app logic has been greatly simplified, making things that were very complex and sometimes had hard to debug errors now easy to understand and reason about. To our surprise, we have noticed even some of the users wanting to already use the beta app, even though it is missing many of the features still, just because it is so stable. Thank you for your time listening to me today. I'm happy to discuss more in detail our experience in GraphQLifying React Native app with you. You can get in touch with me at plrdev on Twitter or GitHub. Thanks.